Is that thing a waveform or a fish's fin? I think I have more work to do here. Hi, I'm Kevin. Welcome to my cave. When I left off in the last episode of the op-amp series, we were looking at a peak detector circuit, a circuit to determine the largest input voltage seen in an interval of time. We found that if the time interval is long, the circuit runs into a horrible problem where the output voltage droops from its peak value. In very short order, the circuit output becomes useless. We need to track down where that voltage is falling. We were working with a circuit like this. When the voltage rises to a new peak, the capacitor should match that voltage, meaning that it will carry a proportional charge. When the voltage drops below the peak, the diode cuts off, and the capacitor should just sit there, charged, holding the voltage. But that's not what we're seeing. I've increased the capacitance from last time by a factor of 10, from 1 nanofarad to 10 nanofarads, in hopes of extending the hold time. But I'm still seeing substantial droop over a period of a few seconds. How bad is it? I've set scope cursors around a 4-second region, and it looks as if the voltage is dropping a little over half a volt per second. That rate of droop corresponds to a current of 5.4 nanoamperes. That's a tiny current, but obviously it's enough to mess up this sensitive circuit. But it's so very small that we're going to have to start looking at non-ideal components. There are 5 possible paths for the current to flow. First, there might be internal leakage current in the capacitor itself. That would show up as a large resistance in parallel with the capacitor. Next, the op-amp inputs don't actually draw zero current, whatever our golden rules have said. Then we have to look at leaky components. The reset transistor might be passing a little bit of current even when the gate is grounded, or the diode might be conducting a little bit even when it's reverse biased. Finally, we have the possibility that the circuit is not completely insulated from the outside world, and there is something conducting a tiny current elsewhere. We'll look at each of these in turn. Before we continue, let me make a brief interruption. Many of you know that my content is never paywalled and is free for anyone to learn from. I never beg for money to support the channel. But I do ask something important, that you take care of one another. To that end, the advertising revenue from this YouTube channel goes to charity. My March 2025 payment has gone to the Get Fed Up campaign of Save the Children. The campaign has a single mission, fighting childhood hunger. Of course, that fight has more benefits, because the prosperity of a community depends on education, and you can't fill a child's brain when a child has an empty belly. But more important, I want children to be able to play and dream about their future without worrying where their next meal will come from. I know that Kevin's Cave people are a kind and generous lot, so I'm urging you to join me in supporting this organization, using the affiliate link up here, or down there, or at any rate somewhere nearby. I've set a relatively modest goal of $500. If even 1% of my subscribers were to give $10 apiece, we'd meet that goal and feed a classroom of 30 hungry kids for a week. I hope that instead we'll just crush it. Won't you help out today? Considering first the capacitor, I'm using a polyester unit, because those are reasonably low leakage. The manufacturer gives a value of at least 30 gigaohms for the insulation resistance. At the 5-volt peak of the signal, that would be a current of only 167 picoamperes. Far less than the 5.4 nanoamperes I'm seeing. I don't think the capacitor is the problem here. Next, let's look at the op-amp input. The current flowing into an op-amp's input is tiny enough that we've been ignoring it up to now, but sometimes it's too big to ignore. The key datasheet parameter you need to look for if you need to control leakage through this path is called the input bias current. This table shows what you can expect from inexpensive parts of each of the three common op-amp types, bipolar, JFET input, and CMOS, and from best-in-class op-amps of the same types. Even though the bias currents are all so small that we can usually ignore them, they still vary by a factor of over 1,000,000. An inexpensive bipolar op-amp, like an LM358, would be entirely inappropriate here. Its bias current might be 50 nanoamperes. That's 10 times the leakage current we're already seeing here. But you sometimes need to watch out for FET input amps as well. Their bias current is temperature sensitive. A JFET jelly bean with a 50 picoampere bias current at room temperature might draw 50 nanoamp bias current if it's running at 100 degrees Celsius in the engine compartment of a car. I should also warn you that the best-in-class amps get that way by sacrificing some other performance parameter. That's why there are so many different kinds of op-amps out there. Because I knew that bias currents might be an issue when I put this circuit together, I chose an LMC6482, which is a fairly low bias current CMOS op-amp, with rail-to-rail input and output, so that the low supply voltage will still allow a reasonable signal amplitude. The datasheet has a nice graph of the input current, showing how it increases nearly exponentially, from 20 femtoamperes or so at room temperature, up to 10 picoamps at the high end of the automotive temperature range. The rule of thumb that bias current of an FET input amp doubles for each 10-degree temperature rise seems to hold up pretty well. In any case, we can likely rule out the op-amp as the culprit for our voltage droop. I suppose the leakage path could be running to the outside world, but I'm really hoping that I won't have to go there. When that sort of thing becomes a problem, designers wind up going to ridiculous extents to fix it. Mounting components on Teflon standoffs or with flying leads to avoid current paths along the surface of a circuit board. Cleaning components aggressively with solvents and then baking to drive off volatile residues to avoid sneak paths along the component surfaces, and various other insane techniques, none of which I'm likely to be able to do on a breadboard demo. So let's just hope for the best. That leaves just the transistor and the diode as possible leakage current sinks. But here we start running into problems with the component data sheets. The manufacturers often don't tell us realistically what leakage currents to expect. They lowball the device's capability, often by orders of magnitude. Now, mind you, I know the risks of going beyond what the datasheet offers. If you do so, you're pretty much committed to incoming inspection of all your parts. I think I can offer you some options that are datasheet compliant, but there are others that a small-time player can certainly get away with. We'll start with the diode. I started with Schottky diodes because I wanted to see how fast I could push this circuit using a relatively cheap CMOS op-amp. But I know they're notoriously leaky, often a few nanoamps at room temperature, or up to a few microamps if you run them hot. They're surely not a good choice for this circuit at very long hold times. Let me start a scoreboard to show how the various diodes perform in this application, so we can keep track of how much we can improve things. The BAT41 Schottky diode that I was using showed a leakage current of 100 nanoamps on the datasheet. We measured a total circuit leakage of 5.4 nanoamps. That'll be the starting point on our journey. Several commenters last time pointed out what I already knew, that Schottky diodes leak like sieves, and suggested using just conventional small signal diodes like the 1N4148. Its datasheet shows a room temperature leakage current over 3 times lower. We'll try that next. I'll pull out the Schottky diodes and plug in some conventional ones. Well, I suppose that's a little bit better. The leakage is down to 3.5 nanoamperes. 3.5 nanoamps is a little disappointing. Not nearly a factor of 3 improvement. Is there anything else we can glean from the datasheet? It turns out that there is a graph of typical leakage current with respect to voltage and temperature, and our 3.5 nanoamp current is a little bit better than what it says to expect. Perhaps the 1N4148 isn't such a great choice after all. There are other silicon diodes that promise much lower leakage. The datasheet for the 1N3595 promises a leakage current of just 1 nanoamp at room temperature. Unfortunately, I don't have any on hand, but I might be able to show you the sort of performance you might expect. You see, back in the day, someone suggested to me that I should try the 1N457 for low leakage applications. It's an older diode that's similar to the 1N3595 and came from the same manufacturer. Its datasheet spec wasn't spectacular, 25 nanoamp reverse current at room temperature. But my friend told me that if you measured a bunch, you could find some with great leakage characteristics. And I just so happened to find a handful that have been lying in one of my parts boxes since sometime in the 1980s. I think they were the ones that I pulled out for being the best for leakage current. Let me see how they're doing, 40 years later. I'll swap them into the circuit in place of the 1N4148s. Now that's more like it. I've extended the scope cursors to measure an 8-second period instead of a 4-second one. The voltage has dropped only 120 millivolts, which corresponds to a leakage current of 150 picoamperes. Let me post that on the scoreboard. Way better than what the datasheet promised. And while this is good enough for most purposes, once in a while you may like to be able to integrate really tiny currents, or hold a voltage for minutes. And it turns out that I have one more trick up my sleeve. Let's look at a JFET. Its schematic symbol gives us a clue. The arrow denotes a PN junction. It means that the gate of the JFET will function as a diode. If we wire the source and the drain together, the equivalent circuit is just a diode. And it's a pretty good one for our purposes. It's reasonably robust. The datasheet shows that it's good for 35 volts of reverse voltage, and we can pass 50 milliamps of forward current through it. But what's cool about it is it has incredibly low leakage. Once again, the datasheet doesn't do it justice. Reverse current of 1 nanoamp is no better than what we've seen already. But once again, the manufacturers lowball the device performance. Let's see by how much. Our circuit looks like this. Now I'm going to pull out the two diodes and replace them with JFETs connected as diodes. I didn't actually need to do the upper diode because it isn't in the leakage path from the capacitor, but I've already made the change in the breadboard. And here it is. I've pulled out the two diodes and added two JFETs in their place. Even stretching the hold time out to nearly 16 seconds, I can't measure any leakage at all with this setup. The trace looks perfectly flat. Okay, I'll replace the 10 nanofarad holding capacitor with a 1 nanofarad one. I'll set the scope cursors up for 10 seconds to make the arithmetic easier. The hold times are so long that this test takes a lot of patience. The trace just crawls across the screen. Okay, I'll wait. After quite a long time, we see that the circuit is losing 40 millivolts in 10 seconds. 4 millivolts per second times 1 nanofarad gives a total leakage of 4 picoamperes. If I had used a 100 nanofarad holding capacitor, I could get the droop down to 40 microvolts per second. I could hold the peak for 4 minutes and still lose only 1/100th of a volt. So that cheap J112 JFET that the datasheet said might leak up to 1 nanoampere was leaking only about 4 picoamperes in my test circuit. Yeah, the manufacturers lowball this stuff. JFET diodes are pretty magical. The lowest leakage current I could find promised for any diode in a quick troll of my suppliers was the PAD1 at 1 picoampere. I didn't bother testing it. I'm almost certain that I'd specify something like that if I were trying to bring a circuit to production. But for a hobbyist one-off, I think this circuit will do fine as it is. By the way, that PAD1 is manufactured on a JFET production line, and the manufacturer hooks it as a JFET diode because diode-connected JFETs are well known for low leakage. The circuit is now performing so very well that I'm convinced I don't need to worry about leakage current in the reset transistor. Which is a good thing, because the datasheet promises only that it's less than a microampere, at 48 volts drain to source. Not very helpful. If you want better datasheet promises from the reset circuit, you could try using a CMOS analog switch IC in place of the MOSFET. The datasheet for the ever-popular 4066 promises a 10 picoampere typical leakage current, and the one for the DG401 series promises the same. So what have we learnt in this experiment? We started with a peak detector that was usable only for very short time intervals, because the charge on its capacitor was leaking away far too fast. We learned a bunch of ways to combat that. First, we learned to look for the input bias currents of our op-amps, and settled on a CMOS op-amp for its low bias current. We learned to use a good quality polymer dielectric capacitor, and control diode leakage by replacing a conventional diode with a JFET. These techniques will be useful in a variety of circuits that have to deal with tiny currents in nodes of very high impedance, so we'll keep them in our back pockets. Next up, I want to tie up some loose ends. I've promised to show you the details of the R2R ladder for digital to analog conversion. I also want to have a quick look at another basic op-amp circuit that uses almost exactly the same techniques as we saw in this video, the sample and hold. Beyond that, there are a bunch of other op-amp circuits to cover. AC amplifiers, current to voltage and voltage to current converters, integrators, differentiators, oscillators, active filters. There's a long list before me. I hope you'll stay tuned for those. If only there were some way for you to suggest to the YouTube algorithm that you enjoy these videos and want to see more of them as they come out. Until next time, stay safe, stay healthy, stay curious, and please take care of one another, like this channel's generous donors to the Get Fed Up campaign: Danielle van der Bent, Andy Kirkham, Charles Lowmiller, Ray Otwell, John Shepard, and 8 donors who wish to remain anonymous. Kevin's Cave people are a wonderful lot. Thank you all. Bye.